everyone, thank you for coming. I'm just going to introduce the speaker a little bit about the topic and then we can get started. Okay, so Dr. Ranadeep Sarkar earned his PhD in physics from the Physical Research Laboratory in India. And for his postdoctoral experience, he relocated to University of Helsinki. And over there, he's been engaged in research till today as well. So his primary research interest centers around the observation and modeling of solar eruptive events, aiming to comprehend their origin and the subsequent space weather effects. So he was awarded a 3-year postdoctoral research grant funded by the Academy of Finland to conduct research on the topic of exploring the formation, evolution, and space weather impact of sheet regions. Additionally, he has also served as a visiting scholar at NASA Goddard Space Flight Center and the Royal Observatory of Belgium. Just a little bit about the topic as well. I'm pretty sure that some of us, especially those who have studied physics here in the audience, know quite a bit about the sun. But it's not only a giant ball of hot plasma. Actually, it is a giant ball of hot plasma, which experiences violent eruptions in the atmosphere. And these eruptions of plasma and magnetic waves can affect satellites and cause severe magnetic storms near Earth space. We need to predict such adverse space weather conditions to get advanced alerts that may prevent the disruption of electric and telecommunication systems in Earth. And in this talk, Dr. Sarkar will share his experiences with space weather forecasting and his current.
So, hello everyone, I am Ranadeep Sarkar. I am doing my postdoctoral research at University of Helsinki. So, the title of my talk today I have kept it like the dark side of the sun, and you must be already thinking that why should be there a dark side of the sun. So, please bear with me, I will slowly introduce you about this aspect of the sun during my talk. So, to begin with, I would like to share briefly my experience with the space science research, that how I came into this field. So, I started my journey with my PhD at the Solar Observatory. You can see there is a beautiful solar observatory surrounded by a lake. So, you might be going to your office by probably taking a metro or bus or something. Sometimes we used to go by boat to our office there. So that used to be our office. And also we had an office at the land site also. So this is a beautiful place where I started my journey during my PhD, and I got fascinated about the study of the sun. Then during my PhD I also got some exposure to go abroad, and I was again more introduced to the observational aspect and the space-based observations of sun in the Royal Observatory of Belgium. Then I also moved to I had physics in NASA Goddard Space Flight Center. Then I started computational modeling of the solar eruptions, and now currently I am continuing the space weather research at University of Helsinki. So yeah. Now to begin with the talk, just let's see a relaxing picture of sunset. So when we think about the sun, so the very first thing that comes to our mind is that sun is so beautiful. It's the source that brings life to this planet. Okay, but when we see the sun through a scientific telescope, then how it looks? It looks like this: a giant ball of gaseous charged particles there, and for this particular image, this is taken from a space-based observatory. So in the goldish color, what you observe, this is the image of the sun in extreme ultraviolet wavelength, and on the background, this black and white image, that is basically the magnetic field map on the surface of the sun, which is on the lowest most atmosphere of the sun, which we call the solar photosphere. The solar photosphere is basically the surface of the solar atmosphere that we can actually observe through our naked eye. Now the interesting thing is that you can see there are in certain regions there are lots of kind of bright things are happening there. And in particular, if you just look at the structures of this bright structure, so you see they are forming kind of loop-like structure. So these kind of loops basically traces the magnetic field lines on the solar atmosphere. And as I said, that this background black and white patches are nothing but the magnetic field map on the solar photosphere. So again, if I just briefly tell you that this the things which are in white, those are the basically direction of the magnetic field lines that are coming towards you. That is the positive part, and the black ones are basically the magnetic field lines which are coming towards this screen. So one is like the positive polarity, and another is negative polarity. And if you just try to see the loop-like structure, so the hook points of the two loops, one point is at rooted in one polarity, and another point is rooted in the another opposite polarity. That means they are magnetically connected on the solar photosphere. And the thing is that sun is magnetically so active, you see. So there are certain, as I already told, there are certain patches on the solar on the image on the solar disk where they are like concentrated. So this part we call it as the active region on the sun. And if you observe the solar image like through your, if you through telescope or your naked eye, sometimes you can identify there are some kind of dark spots, so which are known as the sunspots. So the lots of number of group of sunspots form this kind of patches or on the sun, which are the active regions, and these are the source region from where a very energetic solar eruptions can happen. Okay. So now, when the solar eruptions happens or they erupt from the sun, how do they look like? So here you can see. So again, this is another image of the sun taken at different wavelength, which basically captures some more like cool material on the sun. And here you can see there are lots of regions from where a huge expulsion of solar, huge expulsion of mass from the solar atmosphere can happen from there. So this is like this. So they can be very huge. You can compare this kind of eruptions with the size of the Earth. So you can see if it's the size of the Earth, then you can just compare with how big this can be, like which are like erupting from the solar atmosphere, this kind of solar eruptions. So in these images we can actually see the initiation and also the eruptions of this solar events, and then once they erupt from the solar atmosphere, they try to propagate in the interplanetary space. Then how do we then look at those kind of features when they are already take off from the sun? So the thing is that this is okay, that like from the solar disk we can observe this kind of features, but when it comes to the outer atmosphere of the sun, then to distinguish those features in the outer atmosphere is very difficult. Why is that? Because the outer atmosphere of the sun is very tenuous. The density is there very tenuous. But the light coming from the solar photosphere, it is very intense. Okay, let's imagine that you are like driving a car in a dark road and some car is coming, there is oncoming car, okay, and the oncoming car is like they have just on the flashes, bright light beams are coming towards you. It is very hard to distinguish the feature of that car. But if the bright light is switched off, then you can kind of distinguish the car is coming towards you. The same is happening with the sun. So once like there is a bright light coming from the solar photosphere, you have to occult that particular light in order to see what is the feature in the outer atmosphere, which is much tenuous, much less dense, and that's why emission from the outer atmosphere is very less. So how to do that, or how to observe them? So one of the natural phenomena that we have is the solar eclipse. During the solar eclipse, the moon acts as a natural occulter which can block the intense photospheric light coming from the sun. So once this light is blocked, then the features in the outer atmosphere of the sun, which is called as solar corona, they becomes visible to you. And if you can just notice the bright, like the fine structures of the solar corona, you can guess how this structure resembles to. Can anyone guess? If I say this kind of magnetic field pattern, it is forming. So which kind of magnetic field pattern it is showing here? It's a simple dipole, right? Magnetic dipole. It has a two polarity coming from this end and then again coming back to another opposite polarity. So although it is not, this kind of structure can be there all the time because sun has its own solar cycle. So for some particular period of time, we can actually see this dipolar kind of magnetic field. So the point is that if we want to observe those solar eruptions that we just saw on the disk of the sun, now if you want to track those at the outer atmosphere of the sun, then what we need to do, we need to block the solar photosphere so that we can have the information of the structure the outer atmosphere. But now this solar eclipse is very rare, even we know. But if you want to continuously monitor the features in the solar corona, then how can we do that? Now one thing is that, let's imagine, so you have a 1 rupee coin. If you just place that 1 rupee coin in front of your eye, then actually you can block the sun. So if you have to place a 1 rupee coin in such a way that you can actually occult the distant source of the sun with that 1 rupee coin. So similarly, if you have a telescope, to place artificial occulter in front of the telescope, which can essentially cut down the intense photospheric light coming from the sun. So that we call a coronagraph, that instrument. So with this instrument, which is called as the, so in this way we can artificially occult the sun. So you can see this is the size of the sun, and the size of the artificial occulter is much bigger than that. So this is the size of the occulter. Now once we block the intense light coming from the sun, then we can actually then observe the like tenuous feature of the outer atmosphere of the sun, which is called the solar corona. So now we can see now we can see the big eruptions are happening from the sun. So again, this is a closer look of that. So this eruptions can be captured with the larger field of view of the same capability, that is the solar coronagraph. So these huge expulsions, you can see how large they can be. So they are routinely erupting from the sun. Now, when they so now this is, I have shown you a kind of large field of view within which we can capture that, but not only that, you can actually observe this kind of eruptions from sun to earth, which with a much larger field of view. And also please keep in your mind that the solar atmosphere is not static to a certain height. So beyond that, the solar atmosphere, they are like the temperature is so high that the electrons gets more energetic, and the solar gravity cannot hold those particles. That's why they start to escape from the sun. So that forms the solar wind. So there is a continuous flow of the solar energetic particles in terms of solar wind, and also sun is a magnetized star. So the magnetic field also is carried out with the wind. So that is the continuous flow is happening, and these eruptions, these are the transient flow of the solar wind. Means why I am saying transient, because these are not happening all the time. So let's say 3 or 4 times in a day when the sun is so active. So one is this transient thing, and another thing is continuous flow of the solar wind. So this we can actually observe from sun to earth with spacecraft, which I am showing here. So this is at the very left hand side, this is the size of the sun. So then from here the eruption is happening, and it is coming all the way from sun to earth, and you can actually see this like charged like energetic particles, they are coming from all the way from sun to earth. Now the question is that if this kind of highly energetic particles are coming to the earth, then how can we survive from this? Right? So because they are so energetic. So the answer is that we have the shield. So which shield? This is Earth's own magnetic field. So remember, like you can take away a message after this talk that we talk about the habitability of on this planet as like the three things, that air, water, and light. But the fourth thing is the magnetic field. It's so important. Without that, we cannot survive in Earth. So this magnetic field, Earth has its own magnetic field. This actually prevents the charge, the energetic particles to enter into the Earth's magnetosphere. That's why we are safe. But this shield can break. How does this shield can break? Because there is a natural phenomenon called as the magnetic reconnection. So let's imagine there are two oppositely directed magnetic field lines. So the blue one is like directed towards like down, and the red was directed towards up. If they come close to each other, then they actually reconnect, and there is a new configuration of magnetic field lines occurs. So what happens after the reconnection? All the charged particles carried by this blue actually enters into the red lines. So similar thing is happening when the solar eruptions has a magnetic field component which is opposite to the direction of the magnetic field component of the Earth's magnetosphere. So in that case, the shield will break because due to the opposite polarity, the magnetic reconnection will occur, and all the charged particles they can enter through this red line. They essentially can enter to the Earth's magnetosphere, and they can hit to the two poles of the Earth. As a result, we see beautiful phenomena like the auroras, like which we call the northern lights. But there comes the beast. That is the geomagnetic storms. So when the storms happening, like when this charged particle dumped into the like north pole and south pole, they like keep on moving this to and from motions, and in that way they create one kind of induced current that is called the geomagnetic current. So due to that geomagnetic current, what can happen? It can severely damage the electronic and telecommunication system on space and as well as on the like ground. So here is one example, like on the year 1999 in March, the hydrocubic system in Canada, they actually it lost the electric power, and like 6 million people were there like out of electricity for 9 hours. And like this is the examples of the transformer that got damaged at that particular time. This is not the one example, there are several examples, but before that, so this historical event is known as the day the sun brought darkness. So this darkness I am talking about in my what I mentioned in the slide, the dark side of the sun. It is not there is a physical side of the sun which is dark. It is the aspect of the sun that is dark, and this is the aspect which is the solar storm. So this is called the day the sun brought darkness, and also this was not like one single event. Recently, like in the year 2022, just 1.5 years ago, there was a launch of several satellites from the Starlink satellites, and those satellites got damaged due to the commencements of a solar storm. So that actually is so you can see, you can now you can understand what consequences we can have when we lost the satellites. Imagine, like again, you are in a very distant place from a city. You are riding car and you want to follow the GPS system, and suddenly the GPS system is gone. So you are in a mess. So this kind of severe consequences can happen due to the solar storm. You can lose the GPS signal and other things that comes from the satellite navigation. Again, I would like to show you another extreme event, which is till date the extreme space weather event registered by us that happened on 1859. There was an intense storm that happened, like the source. So this is a kind of image that was drawn by hand by Professor Richard Carrington on 1859. So basically, this image is the image of the on the surface of the solar photosphere that which we can observe with our naked eye. So this is not the whole sun, but a particular cropped part of the full solar disk. So in the mostly what we see, when these solar eruptions are happening, you also see some very bright emission from those source locations. So that bright emissions we call as solar flares. So mostly those solar flares are observable at much higher height on the solar photosphere, not on the solar photosphere, but in the solar corona. But in this particular case, the flare was like so intense that we could also see the kind of signature of this flare on the solar photosphere itself. So this is known as the Carrington flare, or the famous Carrington flare, and also as a consequence we had a huge geomagnetic storm on Earth, and as a result it was reported that the mid-latitude areas over the United States and Europe, they faced a huge problems like regarding electrical shocks and fires, which essentially disrupts their telegraph wires at that particular time. Now, imagine that at that like 1859, at that particular era, most of the like high quality technology was based on the telegraph wires. But now we are so much dependent on the electric and telecommunication system. If this kind of storm happened in this particular time, then consequently the economic loss that we can face, that could be like similar to 2.6 trillion economic loss. And you would probably say that what could be the probability that this kind of storm can happen at this time, because it happened all the almost 150 years ago, 1959. So from statistical studies, it has been found that there is a the probability of this for happening of this character effect in the next 10 years is 12%, which is not a very less probability. So there is a decent probability that this kind of things can happen, and this can disrupt our space-based technology as well as the system on the ground. So now what we can do? So we can work with something like if we want to prevent this kind of damages, then what we can do, we can observe that when these eruptions are happening on the sun, and then what are the characteristics of this eruption, and depending on that we can actually use some computational model to predict those at near Earth with some advanced time. Then we can predict in advance that when this structure is going to come at near Earth space, and what will be the magnetic characteristics of this structure if they are going to reconnect with Earth's magnetic field or not. Because remember, if the reconnection will only happen when the magnetic field carried out by this eruption will be oppositely directed to, as compared to the direction of the Earth's magnetic field. So we can prevent the damages caused by solar storms if we can predict them beforehand. So if you again recall in one of my slides, I showed you that we can actually observe the eruptions of from the sun all the way from sun to Earth, but that will not serve our purpose, because if we wait for those eruptions to come close to the Earth, then if we want to predict, then already you are out of time to get prevention for this kind of damages. So what you need to do, you need to predict those in advance. Therefore, so you have to have used some kind of models, through which you can have the observation close to the sun and then use those models. So at least before 1 or 2 days you can predict those the arrival, because that typically the arrival time for those solar eruptions from sun to Earth is 2 to 3 days. Of course, there are some there could be some events which can be so energetic, can have very high speed, like you can imagine 3000 km per second, that can arrive within 16 to 17 hours from sun to Earth. but at least so that you have to have predict those things beforehand when they arrive at our Earth, so to get the prevention measures. So the thing is that how we can do it, we can use or you can study or form some space weather modeling framework that can serve as a tool to predict those storms beforehand. So what could be the key tasks? So as I have told first one thing is that when they are going to arrive at Earth, so to know the timing first. And then once we know that, okay, we know the timing, but whether it is the magnetic field carried out by this like solar eruptions will be opposite to the Earth's magnetic field or not. That is also the second important thing, because depending on that only the detection will occur and you will have the geometric storm. So the second thing is that prediction of the magnetic field orientation inside that solar eruptions. So how we can execute these two tasks? So first of all, as I have mentioned, that we have to use a modeling framework, but how the models will like work? Like, okay, we know the physics, but how we should like run the model? So we need some input parameters of the solar eruptions, which we can obtain from the remote sensing observations, like from satellites that are orbiting around the Earth, or some satellites which are placed very close to the Earth. So this can have a continuous monitoring of the solar eruptions. So from these observations, we can actually see when the eruptions is happening and at which direction these eruptions are going, and what are the other characteristics of this eruption, through which we can actually prepare the input parameter for our computational model, and then we can use the computational facilities to like propagate or to run more models and try to see that when this structure will like come from the sun to Earth, and finally what will be their magnetic structure and what will be the arrival time of this structure at close to Earth. So in more detail, how do you constrain and observe these solar eruptions close to the sun? So again, this is the image of the solar eruptions, in the outer atmosphere of the sun, which is again the solar corona, which is basically can be obtained using the coronagraph images. So coronagraph again, it is artificially operated operator which is blocking the atmospheric light here. So you can see the features of this structure in the sun, and basically this is their typical three-part structure we call inside a coronal mass ejections. So these are again magnetic structure. So this dark part is basically the inherent like a strong magnetic field part of this solar erupting structure. And when this structure like erupts through the solar atmosphere, it starts to accumulate the solar atmospheric mass in front of it, which forms this kind of bright part, what is the leading edge, and also this kind of magnetic structure itself carries some kind of mass within it, and due to the solar gravity, this kind of mass should be located at the lower part of the structure. So that's why it is, again you see a bright part which is called the core. So this is the whole structure of a like erupting, which is erupting from the sun, and we call it a coronal mass ejections. So when this structure now the motivation is like that, using this remote sensing images, we have to characterize or input parameters for the model, like for example, like what should be the speed of these eruptions. Then we can insert that in our model and try to see what will be the arrival time. Second thing is that the geometry of this erupting structure, whether they are, how wide are they, and so in terms of that, whether they are going to, if they are more wider or narrower. So these kind of things regarding the geometry of this thing of the solar eruptions, and also as I told, another important thing is that magnetic field orientation inside this structure. Right? If it is the orientation is opposite to the Earth's magnetic field, then only it is going to affect or going to create the geometric storm at near Earth space. Now let's say I I will show you this example. How should we measure the speed? So there are images. So, but how we do it that? So these are the images stacked over like at different times. So time is advancing from left to right. So what you can do, you can take different images at different times, and you can take how the leading edge height is evolving with time. So you know the height and you know the time. So from this height time relation, you can estimate the speed. But there could be an error comes from estimating from this kind of speed when you are just using one single viewpoint image. So let's see. So I'm talking about the height of this kind of structure. So let's say if I have a selfie stick and I want to take my picture and I will give you to measure my height. Okay, if I take the selfie stick lower down, I will come with much higher height in the image. But if I take the selfie stick towards like in this way, I will look very shorter in the image. So the measurement of the height will also undergo some projection effect depending on from which viewpoint you are capturing the image, then how you are estimating the height. So it would be very useful if you have observations from different view angles. So then you will get a kind of complete picture of the then if you have multiple viewpoints and multiple images, then you can actually reconstruct the actual height. So that we do from the multi viewpoint. We have this kind of facilities in space. There are multiple satellites and multiple which are giving us the images from multi viewpoint. So once we have the multi viewpoint images, then we can actually see the same structure but from different viewpoints. So we can estimate what is the 3D structure of this event. So basically in this particular thing, you can see 3 images, so which is basically the image of the same structure but taken with 3 different satellites which are separated by this kind of angles. So now mostly the geometry that fits well with this kind of solar eruptions is a kind of Gaussian kind of features. So this kind of structure really crudely, like I would say, like fits well with the solar erupting structure. So we try to fit this kind of geometry with this observed white light features and try to see that if how they should match well for all the observations taken from the 3 different view angles. Once we know the geometry, then we need to constrain again the magnetic field orientation inside those structures. So this is the white light structure, and we also need to constrain what will be the magnetic field orientation, which can be obtained again from the remote sensing observation of the sun. So once we know the magnetic characteristic and we also know how wider is this structure, then what is the speed that we can obtain from that different view angle images. So then we can run this in our model. So basically this is our model output, which is basically showing you the velocity profile on the plane, which is the ecliptic plane. So ecliptic plane, you can imagine so this is the sun, so Earth is orbiting around it. So the plane in which the Earth is orbiting is the ecliptic plane. So this plane is has been shown here, and the color bar is basically depicting the speed profile on this particular plane. And again, I am showing another plane, which is called the meridional plane, which is perpendicular to the ecliptic plane, which is shown here. And this is the location, this is the location of Earth projected on this plane, and these are the different spacecraft orbiting, or probably the different planets, Mercury, Venus. Those are has been shown here. Now, if I run the model, you see these eruptions are coming here, so they are constrained with some input speed, and now we can track that once we have constrained them constrain those eruptions with some input speed, then how they will evolve from sun to earth, and from that we can actually estimate the arrival time of this particular eruptions at earth, and also then I will show you, this is a kind of examples which is not like very perfect prediction, but you can see this, the red things are basically, so what we have done, we have chose a past event, that event which already occurred, and then we try to run our model to validate it. So this is the model results, which is shown with the blue solid lines. So kind of we are getting a decent match with between the observed and the model results. So that's the part about predicting the arrival time. And the second thing is that prediction of the magnetic field structure also. So you can see here we have the complicated like magnetic field structure of the solar eruptions, but we have to do it in order to know the magnetic field orientation inside this kind of solar erupting structure, so that we can understand whether the structure is going to reconnect with the Earth's magnetic field or not. So one thing is that the arrival time of the eruption, and also the same is that the magnetic field orientation inside this erupting structure. On that also we have some kind of handle through which we can estimate. So to be honest, the models are not perfect. So we have to do a lot of work to bring those in a kind of operational tool, and but like, the efforts are going on, and the thing that without which this talk will be incomplete, that is I need to acknowledge like recently, as this is a proud moment for us as Indians, like the Aditya 11 mission, which is India's first space-based mission that has just reached on 6th of January this month to the L1 point, and this will be continuously monitoring the sun, and we are expecting to have very fruitful scientific data out of this. So in summary, like I have shown you that geometric storms are like they can create some adverse condition and near Earth space, and which can damage the satellites, and which can also may cause the electronic and telecommunication, the damage of the electronic and telecommunication system at Earth. So as well, to tackle this, what we are doing, we are like working on to build up a space weather forecasting tool that can provide us an advanced alert about the arrival time of the solar eruptions, as well as the magnetic structure inside those solar erupting things, so that we can predict the occurrence as well as the strength of this geomagnetic storm. So sun is active and this like going things, but no worries, we are working hard on that, and that I'd like